Alright, so the next question is, how do you actually obtain confidence intervals? Okay, and let's say we have some parameter theta for which we want to obtain a confidence interval, which means that we would like to obtain, estimators L and U. Okay, alright, so we'd like to obtain statistics rather, sorry. Like to obtain statistics L and U, which are functions of the data that we observed. Okay. Now the key idea that we are going to use this notion of estimators that we have been looking at in the previous lecture. Okay, so let's say that our observations as before are x1 through xn, and these are all IID. Okay, from the known distribution, right? Parameter theta. Okay, so now suppose we have an estimator, and let's call this estimator t, like we've been calling it before. So t is some function, so this is some statistic x1 through xn, and let's assume that t is an estimator for theta, and it has, and suppose that it has mean squared error, which we defined last class, mean squared error equal to some quantity that I am for now going to call gamma. Okay, gamma is the mean squared error. Okay, so what does that mean? So it means that the expected value of t minus theta whole squared, so this is equal to gamma. Okay, so that's what I'm assuming, right? And I'm not assuming, for example, that expected value of t is equal to theta, right? So not assuming that it's unbiased. Okay. May or may not. That this is true. Okay, so we are not assuming any unbiased. Okay, so if we have an estimator t, and if you have this kind of a property, now the question is, do you somehow automatically get confidence intervals? Okay, so the question is, suppose we know, actually for now, suppose we even know gamma. Okay, suppose we know gamma. Now, can we obtain confidence intervals? Okay, so let us now see why you might expect that something like this should hold. Okay, so let me draw a picture. Okay, so let's look at the key idea is look at, so t is some estimator, right? So t is some estimator for theta, and so t is a random variable. Okay, which means it has some distribution, has some PDF. Okay, so t is something, so if you want to think about how to obtain this kind of a distribution, think that you take many different such samples x1 through xn. For each one you compute t, and you see how this random variable is distributed. Okay, so that's what we've been always doing. Okay, and this represents the probability. This is the PDF, and this is the value of t. Okay, so the x-axis represents value of t. Okay, so there is some mean. So the mean could be this, or the expected value or something. And now the true theta could be something like over here. Okay, I'm not assuming that that these two are the same. Okay, all right. So this is the PDF. Okay, and of t. Okay. Now what my assumption says is that the gap, the expected value of t minus theta whole squared is equal to gamma. Okay, so what does that mean, right? So what it means, or what I would like to claim it means, is that suppose I look at what is the likelihood or what is the probability that t takes values that are more than, let's say some theta plus delta, and or let's say they are less than theta minus delta. Okay, so delta is some length that I'm fixing, and I'm asking this question: what is the probability that t minus theta is more than delta? Okay, the absolute value. Okay, so in other words, t is less than theta minus delta, or t is more than theta plus delta. Okay, so note that this is equivalent to this. Okay, so so these two implications mean that these two statements are mathematically equivalent, logically equivalent. Okay, all right. So this is the question that I would like to answer. Okay, so what is the probability that the absolute value of t minus theta is more than some delta, which I fix appropriately, right? So if we knew the PDF of t, right, so I have plotted the PDF of t, then what I'm asking is that the total area of the shaded region. Okay, so this is exactly equal to the total area of the shaded region. Okay, now the question is, can we bound this total area in terms of this gamma and this quantity delta that we have chosen? Okay, so that's the question that we'd like to answer. Okay, and before answering it, let me give you a little bit of intuition. Okay, so the intuition that I'd like to give is, suppose we choose delta to be equal to 10 times square root gamma. Okay, this choice of square root gamma is important, and it may seem a little arbitrary to you, but suppose we choose this. Okay. Now, now I'm interested in the quantity. What is probability that t minus theta is more than 10 times root gamma? Okay, so this is like saying that delta is chosen to be 10 times root gamma, and I would like to lie out t to be either on this side or on this side, but not over here. Okay, so that's the probability that I'd like to measure. Okay, so note that this is equivalent to asking what is the probability that t minus theta whole squared is more than 100 times gamma, right? Because I'm just squaring this inequality, and both sides are positive numbers, so I can square this quantity. So these two are exactly equivalent. Okay. Okay. So that's so this is the question that we'd like to understand, and I'd like to claim that this probability cannot be too high. Cannot be more than actually 1 by 100. Okay, and so there's actually I will derive this kind of inequality before, but let me give you some kind of an intuition, right? So what we know is that how was gamma defined, right? So gamma was defined as the expected value of t minus theta whole square, right? So on average, right? So on average, t minus theta whole squared would be gamma, right? So on average meaning if I were to do like multiple samples and something, okay, so t minus theta squared would be gamma, right? And now I'm asking you, what is the likelihood that it is more than 100 times gamma, right? Or what is the probability that it's more than 100 times gamma, right? So if you were to think of t minus theta whole square as a random variable, right? So this is a non-negative number, right? Because the square of t minus theta whole squared, it's always non-negative. So this is x equals 0. Okay, so this random variable t minus theta whole squared has some distribution, right? So it can be 0 sometimes, maybe it's 0 with some probability, it's something like that, and then it decays. Okay, but what we know is that the expectation of this random variable is gamma. Okay, and now I'm asking you, what is the probability that it's like more than 100 times gamma, right? So I'm asking you, what is the probability that t minus theta whole squared lies in this interval? Okay, and so this is a consequence. So bounding quantities like this is the goal of what is called Chebyshev's inequality, and that's what we will see just now. Okay, but the main claim that we will show is that this probability cannot be more than 1 over 100. Okay, and the 100 comes because of the same reason as why we have 100 over here. Okay, so let me deduce that formally in the next video.